In today's lesson, I am going to explain how to identify the acidic protons in a given organic compound. There are several main points we have to check to understand this concept. First, let us look commonly used acidic organic compound. Now, this is acetic acid. We already know this is an acidic compound and also one of the most powerful organic acid found in organic molecule. Now, once we remove the acidic proton here, a negative charge will result on oxygen atom. This is the negative charge. Now, to stable this anion formed, that is when this proton is removed, this negative charge should be able to stabilize. In this example, the negative charge is on the electron negative oxygen atom. So we can say it is somewhat stable because oxygen atom likes negative charge. Also, this can delocalize with this carbonyl group and form this resonance structure. Now, these are the factors that enhance the acidity, particularly on given organic molecule. So, then we can see once the proton is removed, the resultant negative charge is going on to the oxygen atom, it is stable, and this anion can form another structure. That means this negative charge can delocalize with the carbonyl group. These two factors make carboxylic acid also more stronger. This is another organic compound. It belongs to alcoholic group. It is ethanol. Now we can remove this proton. Then it forms ethoxide ion like this. When we compare to the early example, this negative charge is also on the oxygen atom, so it is stable. But this negative charge cannot be delocalized with any other group, like in the early example. Then we have to understand that the ethoxide ion is not that much stable. As a result of that, ethanol is not going to be stronger acid, but it can remove the proton, but we cannot see considerable acidity with compared to carboxylic acid. Now we go to this example. This is aldehyde. Now here we have to identify the acidic protons and we have to use the alpha proton concept. Alpha proton is the protons connected to the carbon atom to which attached to the functional group. Now this is the functional group, carbonyl group, and this carbon is attached to this functional group, and all three protons attached to this carbon can be considered as alpha protons. Now there are three alpha protons in this molecule, but at given time only one can be removed. Once we removed, we can get this carbon ion, and that carbon ion can be delocalized with the carbonyl system. Now this is the exact reaction or reactivity that we use in the aldol condensation. I will explain in a separate video that aldol condensation. So we can tell that this aldehydic molecule has alpha protons because the resultant negative charge can be delocalized in the carbonyl system. Not only this aldehyde group, also ketones, if they have alpha protons, then we can tell they have acidic protons. Now we will look the alkyl bromide. It belongs to alkyl halide group. First we have to check whether this molecule has alpha proton. Now in alkyl halide, this is the functional group bromide, and this carbon is directly attached to this functional group. So carbon next to this carbon that is directly attached to the functional group is called as the alpha carbon. So this is the alpha carbon in this molecule, and all the hydrogen atoms attached to this alpha carbon can be considered as alpha protons. Now once we remove this proton, that means one proton, we will get this anionic charge on carbon atom, so we can tell that as a carbon ion. But you already know carbon ions are highly unstable, so there should be a way to stabilize that. The only way to stabilize this is that this Br group will leave in this way. It will result alkene. With compared to earlier example, this is not a reversible process. Once Br leaves, it cannot reattach. So this is going to be totally different molecule. So this reaction is used when we use alcoholic potassium hydroxide with alkyl halide. This is phenol. Once we removed acidic proton here, it results phenate ion. So this anion has more factors that enhances its stability. One is that negative charge is going on to the oxygen atom, that is preferable because oxygen is highly electronegative atom. And second one, this negative charge can delocalize with the aromatic system, so it is more stable. Now this is benzoic acid. Benzoic acid also has hydrogen atom that is attached to oxygen. So we can remove that, resulting negative charge on oxygen. So we can say this is a carboxylate or benzoate anion. Now this negative charge also can be delocalized with the carbonyl system, but not like in the phenol in earlier example, because negative charge cannot delocalize with the aromatic ring. Anyway, this is also going to be stable, making benzoic acid is acidic. Now let us look the summary we have learned so far. We learned how does an organic molecule become acidic. For other terms, whether we can identify given organic molecule has removable protons, we identify them as acidic protons. The fundamental behind this is once the proton is removed, the resultant negative charge should be stable. Now there are main two factors that help to stabilize that resultant negative charge. First one, the atom that is going to hold on that negative charge should be highly electronegative, then it prefers negative charges. We show in many examples, negative charge is going on to the oxygen, so it is stable. Second one, when negative charge result on a given atom, it should be stabilized by resonance structures. These two factors help to organic molecule to become acidic.